Howdy, today on Flippin Science we're looking at fuel cells and recharging. So here are the key ideas in intended student learnings. Fuel cells are galvanic cells in which the electrode reactants are available in continuous supply. Then you need to be able to state the advantages and disadvantages of fuel cells compared with other galvanic cells. And then some galvanic cells can be recharged by using an external electrical supply to reverse the electrode reactions. Then you need to describe the complementary nature of charging and discharging in rechargeable galvanic cells. So what is a fuel cell? Well, a fuel cell, they convert chemical energy from a fuel directly into electricity without combustion, so without burning. The electricity is produced constantly as long as fuel is being supplied to the electrodes. And let's look at an example. We're going to look at a very simple example called a hydrogen-oxygen fuel cell. This is a hydrogen-oxygen fuel cell. They've been used for a long time in space exploration. The reason for that is one of the fuels to get up into space is hydrogen. And the crew require oxygen to breathe. So we've got hydrogen and oxygen, so you can use those to make electricity. So this is a fuel cell from an Apollo spacecraft that went to the moon. So here's a picture of a hydrogen-oxygen fuel cell and a bit of an idea about how it works. You pump hydrogen in one side, use oxygen from the air in the other side. The hydrogen splits and produces electrons. Those electrons travel through the external circuit and you can use them to power something. The hydrogen ions travel through, I should say. They regain their electrons on this side. They react with the oxygen from the air and you produce water vapor as a byproduct. Here's another picture of a hydrogen-oxygen fuel cell. So hydrogen gas comes in one side, oxygen gas comes in the other. At the anode you get the hydrogen splitting, you get hydrogen ions travelling through the solution. They reunite with the oxygen on this side and you get water being produced, and that's down here. In the middle you have an electrolyte, so in this case it's potassium hydroxide. That allows the hydrogen ions to travel from one side to the other. Here's an animation showing how a hydrogen-oxygen fuel cell works. So the hydrogen coming in from this side, this is our anode. Electrons are being stripped off of the hydrogen ions pass through, and we get our water being produced on this side of the cathode. So hydrogen-oxygen fuel cells have been investigated to be used in cars for a little while. Here is a Mercedes F-cell car. Here is an FC, so fuel cell stack from a Toyota car. Ford got into the action, and here's a really small one. The size of these things can be large or small, it depends on what you want to use them for. So they have been in development for a while. So here's the Redox Equations for the hydrogen-oxygen fuel cell. So at the anode you get the hydrogen being oxidized. This hydroxide here, that's the potassium hydroxide, the electrolyte that we were looking at before. So the hydrogen gas is oxidized and you get electrons being generated. At the cathode you're getting the reduction happening, so the oxygen is being reduced to hydroxide ions. But the hydroxide ions cancel out over here. So what you end up with is water being produced. So the overall equation is you're reacting your hydrogen with your oxygen to produce water. So it's, like I said before, it's the same as combusting hydrogen and oxygen to produce water, but rather than generating heat to do that, we strip the electrons off in a separate reaction. There's another few different types of fuel cells. So this is an aluminium air fuel cell. So oxygen from the air is oxidizing aluminium. There's problems with this. One of the problems is you're using aluminium to generate electricity. You don't get that aluminium back in a readily available format, and aluminium is very, very handy. It's one of the most widely used metals, and it's very easily recycled. So this isn't used very often. So another fuel cell is called the solid oxide fuel cell. The solid oxide fuel cell can use a variety of fuels depending on what's available, really. Using oxygen on one side, like we had with the hydrogen-oxygen fuel cell. Here you can use hydrogen, you can use carbon monoxide, you can use methane. So this one's handy in that a variety of fuels can be used. So here's a picture showing the solid oxide fuel cell. So in this case we're using hydrogen and carbon monoxide as our fuel on one side and just oxygen on the other. And again, so at the anode these are being stripped of their electrons. Those electrons are being used to generate the electricity over here. Well, they're generating the electricity as they flow. And as they return to the oxygen you get your waste products being produced. This is a stack of fuel cells. Here is a large whole heap of fuel cells joined together to generate usable amounts of electricity that could supply a home or a business. So they're stackable. The more fuel cells you have joined together, the more electricity you make. Here's an example of a stack that I was talking about. So you have an interconnector, you have your anode, you have your electrolyte, and you have your cathode. These spaces allow for you to pump your fuels in. So one fuel going one direction, one fuel going the other direction. And then as they meet at that boundary between the anode, the electrolyte, and the cathode, that's where you get your electricity being produced. It's very porous, so there's lots of holes with lots of space, and that's so you can have things like catalysts laid on the surface here. It allows the gases to pass through as well because you've got holes. So what you need to be able to do is describe the advantages and disadvantages of using fuel cells compared to regular galvanic cells. One of the advantages is, as long as you're supplying fuel to the anode, you're going to generate electricity. With a typical galvanic cell, as soon as your anode breaks up and is turned into its ions, then you can't use it anymore unless you recharge it. You're not burning fuel, so you're not generating large amounts of heat necessarily from the combustion process. The only product, if we're looking at a hydrogen oxygen fuel cell, is water vapor, which is better for the environment than, I don't know, if you're using petrol, for example, better for the environment than the carbon dioxide, carbon monoxide, particulate soot, and so on that are being produced from a petrol engine. The other way of looking at it is compared to a galvanic cell, you're not throwing out a battery at the end of its use. You can reuse it as long as you can supply fuel to it. Hydrogen is very abundant. It's one of the most abundant elements, well, it is the most abundant element in the universe. And their efficiency compared to burning diesel or burning gas or burning petrol is really, really high. Again, this doesn't really relate to a galvanic cell, but you get more energy out per gram of fuel from a fuel cell than you do from burning it. Disadvantages, since they run on hydrogen, if we're talking about a hydrogen oxygen fuel cell, there's no really easy and efficient way of generating hydrogen. We have lots of water which contains hydrogen, but in order to get that hydrogen out, you have to put electricity in to break up the hydrogen away from the oxygen. And that requires energy to break it up, and then you don't get that amount of energy back when you use it in the fuel cell. Nothing is 100% efficient like that. So just producing the hydrogen at the moment, oftentimes we just strip it off of methane and other natural gases, and that's bad for the environment because it generates carbon dioxide anyway. At the moment it's very difficult to transport hydrogen because we don't have the infrastructure to do that. It's a gas, it's a very small gas, so it can leak out easily from containing, and it's also quite flammable. So we need to have a distribution method to distribute hydrogen all around so it could be used very easily. Like I said, storage, it's a very small gas, so it leaks out from the gaps between whatever storage medium you're using. So in a metallic tank, the hydrogen can leak out of the tank slowly over time. They're very expensive to produce, fuel cells at the moment. They're a new technology. There's not really a big scale in terms of their production. So because of that, they're expensive to produce at the moment compared to, say, a galvanic cell. And it's a very, it's a technology that's been around for a while, but it hasn't really progressed as far as we would like it to. At the moment, we just can't use it in a way compared to using petrol to power a car, or even using electricity in typical galvanic cells in electric cars. We don't have the distribution system to run it. The other thing we're going to talk about today is the nature of charging and discharging batteries. The reason why batteries go flat, and this relates to our discussion about fuel cells, is because your anode gets corroded. It breaks down and it goes into the electrolyte solution. So here we have our zinc copper Daniel cell that we made. The zinc is the anode, so this is going to break it down from zinc metal into zinc ions that will go into solution. And once that happens, you don't have a source of electrons anymore, so you're not going to generate electricity. So I've got a wonderful animation here which should show the anode disappearing. There it goes. So once the anode disappears, you don't have a source of electrons anymore, and the battery won't generate electricity. Now, the normal batteries you have in your devices don't look like this. They're not two cells connected like this at all. But the idea is the same. Once the anode has been broken down into its ions, it doesn't generate electricity anymore. So that's why your battery goes flat. Now, depending on the type of battery, they can be recharged. And the way that this is done is by reversing the current flowing into the cell. So the battery discharges and you have your anode being oxidized. If you put electricity in, you can reverse those reactions. So your anode, which was oxidized, can then be, the ions from the anode can be reduced back to a new anode, and then you can discharge your cell again and again. So if we look at our zinc copper cell here, I've got a little bit of anode left over. I'm going to put in energy, and that's what this symbol here is. That's showing a battery. So I'm going to put in energy, and hopefully, if my animation works, we should see the anode being rebuilt. Look at that. Isn't that amazing? So what I'm doing is I'm turning the zinc ions from the solution back into solid zinc on my anode. By forcing the electrons the other direction, we're making what wasn't a oxidation reaction a reduction reaction. We're reducing the zinc ions to solid zinc to rebuild our anode. And once we've done that, we could reuse this again. Now, in your typical devices, you're using a lithium-ion battery in your mobile phone, say, or your laptop. But the idea is the same. You're putting in electricity when you're charging your battery. You're reversing the typical reaction, which would be the oxidation of your anode. You're turning that into a reduction reaction to regenerate your anode. So today on Flipping Science, we looked at fuel cells and the charging and discharging of batteries. That's it for Flipping Science today. See ya.